So I'm working on lattice QCD mainly, and I want to apply the machine learning to lattice QCD. And I'm working on maybe 5 years for this topic. And I'm working on the neural network thing and axial anomaly at high temperature. And also recently I'm working on Schwinger model on quantum computer. And recently I published a book about deep learning and physics. This is published in 3 years ago in Japanese, and this is translated version in English. Okay, so this talk contains 2 topics. The first topic I would like to explain that our how to say, the invention, kind of invention, the neural network and the symmetry, the gauge covariant neural network. And the next one is that application of the gauge covariant neural networks, the self-learning HMC. And some of my contents are very introductive. Maybe most of you know, but just in case, let me explain. Okay, so let me start from very basic thing. So most of us are interested in QCD, and QCD is described by this really simple Lagrangian action, and every quantity is calculated by using this Hamiltonian. This is nothing but just a generalization of QED, and this action gives that all of the information of our subatomic world around 100 MeV. This gives us information of the equation of state and critical temperature for coherent plasma and force between nuclei, and etc. Of course, we know that property of the G, the G is too large, so we cannot use a perturbation. We have to use that some technique, and we employ the lattice regularization to calculate this one. And both of them has the same information for the long distance, and that how to say, that action is converted in this form. Yes. And on the lattice, the gauge transformation are slightly modified in this form, the right-hand side, and the continuum degrees of freedom are transformed using this kind of 2 terms transformation. But on the lattice, gauge transformation defined on the bond, and the gauge transformation is defined on the point. And if the links has same starting point and the ending point, that the gauge transformation are same. I will use this fact. And by using the lattice QCD, already we know that the lattice QCD gives us some quantitative information of the hadron spectrum and tell us that the critical temperature. There are so many things to calculate using lattice QCD. Oh, by the way, so we recently made a public code on Julia, a lattice QCD code in Julia language. So I will use this one. And Julia is a kind of a new open source scientific language. And this is faster than C and Fortran, and productive as a Python. And I want to emphasize this one, that Julia is a machine learning friendly language. So Julia has own machine learning packages, and also it can call that the Python libraries through a PyCall function. And also most of the supercomputer supports Julia. So this is, I think, useful for this community. And in our code that we support that SUN heat bus and the self-learning Monte Carlo and the SUN Stout, the Staggered RHMC and the Wilson Clover HMC, and Savon measurement. And if you are interested in, please try from this link. Okay, let me move on to my contents. So I'm interested in the gauge symmetry. How can we deal with the data with gauge symmetry? And how can we embed the gauge symmetric neural network in full HMC? So this is kind of common knowledge that global symmetry is easy to treat. For example, the image recognition case that the translational invariance can be dealt with a convolution. I will explain later. And by using convolutional neural network, so we can easily classify this one, this kind of images. And if the data has a global symmetry like Z2 for the Isaac models, then conventional neural network architecture works well, and it is very widely used in the condensed matter physics. And this is a kind of private motivation for this work. I wanted to make the gauge symmetric neural network since 2017. I put this paper on the archive 4 years ago. And in that paper, I mentioned that we must guarantee the gauge symmetry of probability distribution for the model to make the correct distribution and or correct configuration of the gauge theory. And what we found is that gauge symmetric neural network is nothing but a trainable smearing. I will explain later. But so this is what we found. And after that, I explained that our use case or demonstration of gauge symmetric neural network. And we compare to the HMC, then we got a consistent result from the HMC one. Okay, let me explain that neural network, the filtering and the convolution. This is kind of basic stuff. Maybe almost most of you guys knows about that. Okay, let me move on. So let me explain from the structure of neural network. So neural network is a composite function, and that the part is it consists by two parts. One is that affine transformation, and another one is activation function. This is an element-wise local function. And affine function is that just a matrix multiplication plus addition of the vector. And the result of the affine transformation is fed to the element-wise local function. Then we get the next one. And this outcome is fed to the next layers X. So then we can repeat as much we want. This is the structure of neural network. And this is schematically written in this form. As you can see, this is nothing but just a composite function consists by the affine transformation and the nonlinear function. And throughout this talk, I will use this notation. Theta represents a set of parameters like the element of this weight and bias term. And the neural network makes a variational map between the vector to vector. So this is the easy example of the typical usage of the neural network. So we can regard picture as a vector, right? So picture is consisted by the bunch of the pixels, which contains the numbers, and we can make a flattened operation. Then we get some vector in 100 times 100 case that this vector is at the 10,000 dimension. On the other hand, if the classification problem is a binary classification, we have two labels, and we can assign that two-dimensional vector to the label. So in this case, that the dog is 0, 1 and the cat is 1, 0. And what neural network does is that make a map between two vector space. And one vector space for left-hand side is that vector space for the picture. And this is 10,000 dimension. And the one picture gives that one vector here. And maybe another cat picture gives that this kind of vector. And the neural networks transform this vector to two-dimensional vector in this way. And then we compare to the resultant vector to the axis. Then we can say that this image is a dog, or this image is a cat, or something like that. And there is a fact called universal approximation theorem that tells us that the neural network can mimic any function in certain limit. In this example, neural network mimics a map between the images and the labels. Okay, let me move on to the explanation of the convolution. The top example in the top is that image filtering. So if we use that Laplacian filter, this is implemented in the Photoshop, and this is nothing but the discretization of the Laplacian. And if we use the Laplacian filter on this image, we can get the edge of the image. So this means that the Laplacian filter is at the edge detection. On the other hand, the convolutional filter is nothing but a trainable filter. So this means that the element in the filter is a trainable. And if we perform the convolution filtering with two trainable filter, we get some images that depends on the training. Yeah, for example, that some filter gives an edge and some filter gives a smoother image on that, if the filter are trained as a Gaussian filter. So this is happened in the convolutional network. And we can, of course, we can stack that structure as usual neural network, and we can repeatedly apply this trainable filters. Of course, the filters can be different in each layer. And this historically, the convolutional layers are inspired from the visual cortex in our brains, maybe animal brains. And the filtering operation does not care the absolute of the coordinate. So in this sense, that the convolutional layer helps to proceed the information of the data with translational symmetry. So neural network should recognize both are those, right? And this is kind of historical and also hand-waving argument. And the modern viewpoint were given by Tako Koya and Max Rank from 2016. So convolution is a concrete example of equivariant layer. And so translation equivariant means that if input is shifted to right, output shifted to right. The translation equivariance help to make the invariant neural network. For rotational symmetric data case, that the neural network force should respect the rotational symmetry. And the framework so-called spherical convolution can treat that rotational symmetric data. And the spatial convolution realizes an approximation which guarantee to have an equivariance of rotation. And here I want to explain that what is the convolution here. So maybe this is two lecture-ish slides, but it is worth to share this knowledge, I think. And the example in the top is that a fully connected version of the one-dimensional data processing. And one-dimensional data means that just a vector, input is a vector, and the vector is fed, and we get the output vector y, the 5-dimensional vector. And if the element in the vector x is shifted, output is randomly changed. There are no, significant information can be extracted from the y. On the other hand, this is a convolution. This is a special case of the weight sharing and the translational equivariant. And so you can see that this is very sparse, and most of weight are shared, same value, band diagonal. And if input, this is input and the bottom is output, and if input is shifted, output also shifted. They move same direction. They transformed in same way. So the element of x, vector x is shifted, output is shifted same way. This is so-called equivariance. And of course that, and after a bunch of convolution, we can summing up the outcome of the this stacked convolution. Then we get the invariant output. So translational equivariance makes that the translational invariance. So this is, yes. So convolutional procedure makes an equivariant map, and the summation makes an invariant output. In this case, that the output of, summation of the output of this one and this one are same. So this means that this neural network is invariant under translation of the input data. So here I put the QFT analogy. So if field phi is locally transformed, d mu phi is a covariant, and this bilinear form is invariant. This is a kind of analogy in QFT. So this is a summary of terminology. So there are so many symmetric things. So I just pick up the how to say example from here. So invariant means that the function f is a scalar for the transformation g, and g is a transformation for the input image, and function f doesn't care anything on this transformation. And equivariant means that as we have seen that transformation g is commute to the function f. This is equivariant. And covariant means that this is kind of commuting, but this can be different from the original g. So this is kind of familiar stuff, because that in the case of adjoint fermion, if we apply the gauge transformation, that the adjoint fermion received a different transformation. It depends on the representation, right? So this is a summary of terminology. And if we choose that a g prime as a g, so it will go back to the equivariant case. And or maybe so I should put this one. G prime is a scalar case, it go back to the equivariant. Invariant. Okay, let me move on to the smearing. So in the if we have the coarse image, rough image, and we can get a smoother image by applying the Gaussian filter. And if we want to apply the numerical derivative on image, that the numerical derivative is unstable for coarse image, but the smoother image has a nicer outcome of the numerical derivative. And also long distance behavior got improved. And we want to have the smooth gauge configuration with keeping gauge symmetry. And of course, we know that we have two choices. One is called Ape smearing, and the other is so-called stout smearing. And most of you guys know that very much about this one. And Ape smearing procedure is something like this: the summing up the link and staple, and two of them has a same transformation property under the gauge transformation, because that the starting point and the end point are same. So this is how to say it. This shows the same gauge transformation law. So this how to say the smearing procedure itself is covariant. And schematically, this smearing procedure is drawn like this: the link plus associate bracket. Then, and we have to project or normalize to the link, because that the result of this summation is no more on the gauge manifold, so we have to project back. And in the calculation graph, this is used in the neural network context, and this is something like this. The input is a gauge configuration U, and it's duplicate in here, and one of them are input of the here this addition, and another is input to the construction of the staple, and added them and project them, and we get next one, and we can repeatedly apply this smearing procedure as usual. And the stout one is at a slightly complicated one, but this is widely used. And the stout smearing is something like this. So this. So we constructed the bracket term and make an anti-Hermitian traces operation. We get Q and exponentiate them and multiply that to the bare link, thin link. So then we get the fat link. And also this is the gauge covariant procedure as well as before. And schematically written in that like this, the fat link is equal to link multiply exponential to the bracket. And in the calculation graph, this is drawn like this. U is duplicated here, and 1 is just added the afterwards, and the remnant one is multiplied to exponential Q. Then we get fat link. And both procedure is summarized in this form. And U plus some gauge, some gauge symmetric function here. So in uppercase, this is stable. And then if we add two of them, this resultant Z mu is input to the some local function here, and then we get fat link. And this fat link can be input of the next one. You know, so we can repeatedly apply the smearing. So at that time, I realized that this has a similar structure to the neural networks. So as we have seen that the neural network is a affine transformation and local transformation. So in this picture, the neural network transformation is nothing but the kind of evolution of the scalar field because it has only one space-time index. Or multi-level smearing is a kind of deep learning with given parameters. So to make it clear, we have to describe that how to train the neural network in this form. Okay, let me move on to the covariant neural network. This is nothing but a trainable smearing. Again, this is a smearing, but written in slightly different form. How to say, to make it to see that the explicit form of the weight is embedded in here. And this is our covariant neural network. This is nothing but a smearing with trainable parameters. And we can use in this way, the U is at the thin link and input to the some smearing and input to this another smearing. So then we get the slightly modified or smeared one. It has not been smeared one, but yeah, we get some modified gauge link as an output of the neural network. So this transformation has a good properties. Obviously, this is the gauge covariant and the translational equivariant and the rotational equivariant. And this makes a map between the gauge field to the gauge field. And this is trainable. This is important. And this W and the W2 can be determined in the training. This is an analogy to the conventional convolutional neural network. As I explained that the figure or picture is fed to the convolutional filter, and we get some edge or maybe smoother image, but it depends on this one. But anyhow, we get the some image, and this is fed to the neural network through a global averaging pooling or flatten. And then we can process the data and we get some result, and we compare the answer to the output of this one using some invariant loss function. The gauge covariant neural network works similarly. I got several questions here. Okay. I can the universal expression like still like that's a good question. So I think this has to be shown. So I hope that this has a universal property, I think, because that there are how to say some wide class in the neural network has universal approximation property for certain limit. Maybe deep, how to say, deep limit has a such kind of thing, I guess. And also the Ape, 1/6 in Ape. This is convention. And we just replace W1 to, how to say, W here instead of 1/6 factor and 1. So we don't use that 1/6 here, alpha/6 here. We don't use that. Someone has a good reference. Maybe 27. 26. Thank you. What and what? Between the equivalent and different, I've seen that being used as maybe this, I don't know, but so Taco, I said that the Taco Cohen and Max Welling start to use that equivariant, and this terminology is rigorous usage of the this definition is a rigorous, I think, mathematically rigorous. And okay, let me go back to my talk. And so gauge covariant neural network is a parameterized smelling. This realizes that the map between the configuration to configuration, and the configuration is fed to the covariant neural network in this something like this. So this is a stout type, and there are two parameters here. For example, this is the not a unique choice, but just for explanation. And there are two coefficients determined in the training and modified into the other form, other configuration. And this can be fed to the Dirac operator. So then we get the parameterized Dirac operator. And this then we can construct a Fermion action or pseudo Fermion action. And then we get a parameterized invariant Fermion action. And this can be fed to the loss function. On the other hand, we can construct loops using the this modified one. Then we get the parameterized loop operator. So this can be Plaquet or Polyakov loop or whatever. So we can construct any loop operator by using this smeared link. And we can construct a bracket, and this can be fed to the loss function. And maybe we can construct a topological charge, and we can input to the loss function. There are many usages, and of course we can stack this one as much as you want. Then we get some parameterized Dirac operator or parameterized loop operator. And this can be used, this is just a parts of the neural network. And then this is a repetition. So we can use that, we can use this neural network to parameterize the action. So bracket gauge action and bracket action plus rectangular, and of course we can use the two different neural network here and here. Or this is another example. We can use the neural network to parameterize the staggered action. We can construct the gauge invariant, rotational invariant, translational invariant, rotational invariant actions through using this covariant network. And we can construct a loss function using some familiar loss function. This can be a mean square or whatever you want. And of course, we can use that gradient descent as usual, and we can use that adaptive momentum optimizer as usual to train the network. And the update or training can be done in this form, that this reputation. This theta is at the parameter in the else layer, else smearing, else step over the smearing. And the parameter is updated by a derivative of loss function with respect to theta. And if we get this derivative, we can update this theta. And then our weight is converted to the some minimum. And to execute this procedure, we need this derivative. And this is usually done by a delta rule. But in our case, that this derivative contains a matrix field. But we know that one because that this, how to say, the derivative with respect to theta is expanded in this form using a chain rule, L derivative L over F and F over S and S over U and something like that. And only this part is non-trivial in other people in other fields. But we know this one. So this matrix derivative is that common to the Stout force. So we know this one. So then we know this one, and this is easy to calculate, and this is trivial. Then we can calculate this block. Then we can calculate this derivative, and then we can execute this gradient descent or Adam or whatever. And we call this, how to say, extended delta rule is that extended rule. I put every derivation in the paper. And I explained that another thing in our paper, the relation to the neural ODE. So this is a kind of the most famous neural network architecture, so-called ResNet. This ResNet has a special connection, so-called skip connection. And this is an input vector, and this is deprecated in here. And one of them are input to the another neural network. And the other is input to the, how to say, added to the output of this G. And then we get next one. And this is 2015. And 2018, some people take a continuum limit of this ResNet, and they got a neural ODE. This is written in this form. This T is a continuum version of the num index of the layer. So this describes the evolution by this neural network. So we know this structure, right? So this is our gauge covariant neural network. This has a same structure. And we can take a continuum limit of the layer direction. And that written in this form. And this form is so-called gradient form. But this not has to be written as a gradient of something. This is just the evolution function or evolution of the function or evolution of field without some local kernel. And this factor itself is mentioned in this Lucia's first paper. Continuous Stout smearing is a Wilson flow. Wilson flow is a continuous version of the Stout smear. Yes. So this is a short summary of what we have done. And the convolutional conventional neural network is on the top, and our covariant neural network in the bottom. Symmetry. So convolution, how to say, we can treat that translation using convolution. And if fixed parameter, convolution neural network work as a filtering, Gaussian filter or Laplacian filter or something like that. And if we take a continuum limit of the ResNet, we get neural ODE. And we can train the neural network by using delta rule and backpropagation and gradient descent optimizer. And the gauge covariant neural network case that we can treat that gauge symmetry in a covariant way, and the translation equivariant, and the 90 rotation is equivariant. And if we fix the parameter by hand, it gives us smearing. And the continuum limit of the layer is the gradient flow. And we can train the neural network with the extended delta rule and back propagation and gradient descent optimizer. And we can reuse that Stout force subroutine. So implementation is not so hard, just add some lines. And we don't need to use that machine learning library to use this framework. This is, I think, advantage of this framework. We can use that lattice QCD code, optimize lattice QCD code. And next, I will show a demonstration. One typical, maybe not typical, one usage of the gauge covariant neural network. This is just a demonstration. So yes, so we are interested in the QCD, and every observable in the QCD is written in the path integral form, and this is converted in this action. And as we know that this integral is at more than 10,000, and we cannot use that Newton cost type integral to control the error. So we use that Monte Carlo instead. So Monte Carlo integration is that we use that some probability is described by Boltzmann weight. And if we use that hybrid Monte Carlo, we can sample. We can make a sample of the gauge theory. And after correcting the configuration, we can calculate the expectation value using the average over the configurations. And this procedure gives that the exact configuration, right? And if we correct as many configurations that this error bar shrinks square root of 1 over square root of n sample. So the average is average will approach to the exact expectation value. This is exact algorithm. On the other hand, neural network is just an approximator, right? So how can it be exact? This is the problem. Yes.
Akio, do you have much left? Because we're over time.
Okay. Yes, I will.
Can you try to wrap up?
Oh, okay. Thank you. Okay, so this is some historical view of the machine learning with configuration. And we tried to generate configuration for 2D scalar in 2017. And after many people working on this one, and last year I developed the self-learning Monte Carlo, and this year I developed the self-learning hybrid Monte Carlo, the non-average gauge theory with dynamical phenomenon in 4 dimensions. So our problem to solve is that, so can we mimic a different Dirac operator using neural net? So our artificial example question is that they put their staggered Dirac operator with mass is 0.3, and we want to try mimic this Dirac operator by using same Dirac operator with neural network and heavier mass. So we want to mimic this one. This is the schematic picture of the self-learning hybrid Monte Carlo. So this is above is at the usual HMC, and the HMC case that the EOM in the molecular dynamics and the metropolis test uses the same Hamiltonian. But on the other hand, self-learning hybrid Monte Carlo uses different Hamiltonian in the molecular dynamics and the metropolis test. Metropolis test has to use that exact one, but EOM is used that parameterized one. But this is exact algorithm because of the metropolis test. This is a summary of this setup. Let me skip. And we use that 3-layered neural network, 3 levels stout, how to say, 2 levels layered stout. This contains 6 trainable parameters. And the loss function is that parameterized action minus exact action. This is a loss function. And we trained the neural network in the prior HMC run. And after that, we performed that SLHMC run. This is a history of the loss function. It's starting from the more than 80, and after the training, it approached to the order 1 value. And this L can be regarded as the Boltzmann factor or reweighting factor. So then this means that without the training, there are no hope to get their configuration. But after the training, we can get some legal configuration. So this is a result of the SLMC, HMC, and HMC. And as you can see that both give that consistent result, even they use a different Dirac operator. And this is a summary slide. My comment is that we found that trainable smearing is at the neural network. And we performed that simulation with the dynamical fermion with machine learning, and we get a consistent result. Okay, thank you very much.
Thank you. So we're a bit over time and we had some questions during the talk. So let's take one. I see there's one in the chat from Leo. Do you want to unmute and ask it yourself, or I can read it? Okay, I'll read it. The question says, can this approach work for the sign problem in the finite density fermion case? And why choose MH equals 0.4, not 0.5 or others?
Okay, so first approach, first thing, we cannot use that sign problem in this case because this is basically on the usual Monte Carlo scheme. But on the other hand, that if we use that two color case, there are no sign problem, but there is some instability and along with that chemical potential direction. At that case, that maybe we can use a self-learning Monte Carlo instead. This is the variation of the self-learning hybrid Monte Carlo, but this doesn't use that pseudo fermion. So I think that works well. I'm not sure. And another thing that why choose the 0.4? So we performed that. Actually, we did some experiment with a different mass, and 0.4, 0.5, 0.6, up to 1.0, and all of them are given the consistent result, except for the the difference is that the acceptance. If we use the larger mass, that acceptance become low. But even though that the result is consistent, and that is written in our paper.
Okay. Okay, let's take one more question from Harvey.
I was just wondering how much faster the new algorithm is.
Okay, so that's a good question. So first I should say that this is not fast. So this is because that our target action itself is a non-smeared action. And on the other hand, our approximate action uses the smearing. So there's big overhead here. So if we use that smearing here, some regular smearing here, and we use a neural network here, at that case that the cost-wise, they that the time the cost of them are almost same, I think, because the procedure is same. So this is just an application, just a use case of the this covariant neural network.
And Hartmut?
Yeah, I was just wondering how realistic your parameter choice is with respect to sort of real QCD. I mean, how close are we to approximating something that has physical relevance?
No, this is just a toy example. So okay. Many people use the working on the two-dimensional QED, right?
Yes.
So this is a similar thing. So we work on 4D, but it's very far from the physical point. Of course, we can use this network in the physical point, but that too costly, right? to
Yeah, yeah.
how to
Okay.
train the network and also to test a bunch of different parameters.
Thank you.